just don't expect that they get to return the next class period all the time. Though that is always my goal. This semester I am doing, well, this year I'm doing division chair, teaching a couple of classes on campus. I'm teaching a couple off online. My load is pretty heavy, so I'm trying to be super efficient, and so I was beyond my wildest dreams that I even got a grade the same day, and that's great, but don't count on that always happening. But it is my goal. If it's not return the next class period, it always will be the following class period. Now, if you're looking at your exam and you want to know what the scores mean, let's look at these real quickly. First of all, there's a score out of 63 points at the top. Score out of 63 that's shown on your exam booklet. That score is the score that you received in the multiple choice portion of the exam. Because, of course, if there are 21 questions and each are worth 3 points each, you take the number of questions you had right, multiply it by 3, and that gives you a score out of 63 points. Then there's a second score there out of 37 points. That is the score on the handwritten portion of the exam. So that number, again, was 37. What I did is I took the number that's in the lower right-hand corner and I subtracted that from 37. And that number in the lower right-hand corner on the front page, that number represents the number of points that were deducted from all of the handwritten pages. And I got that by summing together the number on the lower right here of page 3 and the lower left of page 4. So again, these numbers that are in the bottom corners, that's the number wrong on each page. And the one that's on the front cover represents the sum of those on the handwritten portions. They were subtracted from 37. I do this all in my head very quickly. I have made mistakes in the past. It's not common, but I do all addition, subtraction, whatever very quickly. It is possible that I'll make an error. If I did, don't let me know now, let me know after class, and we'll fix it. I do not go through exams in class. What I do, however, is I post the answer key on the bulletin board outside of the classroom right after the exam. So if you missed it, I did try to catch everyone here as they left for the day and did post it out there. If you did not take a look at it, I'm carrying it with me right now. We do have office hours right after class. You're more than welcome to sit down with me and go through the answers or go through your exam with me. I always believe that by going through these on an individual basis, I can more tailor my feedback than going through the exam for everyone. Some people getting the entire exam right, and I'm just wasting the time of those people that did well. So I can much more tailor my help to you on an individual basis by going through it with you one-on-one. The scores in here range anywhere from a 56, I believe, up to a 100. Now, if you're patting yourself on the back right now, I wouldn't be patting yourself on the back too long, because what's often happened in the past is that people will say, oh, geez, you know, this is all I really need to study. I'm not going to study any more than I have. Get a little complacent, and then they get killed on the second exam. And the second exam in here is actually the toughest exam of the semester, not this first one. So if you are feeling like really good, I mean, it's all right to pat yourself on the back. I was really pleased with the scores in here. And I think almost everyone, if there was one person got like the temperature conversion problem right, I mean, if that person would have gotten it right, it would have been the first time ever that everybody had gotten that temperature conversion problem right in here. So I'm pleased about that piece in here. And if you're that one person, whatever, I mean, you've had plenty of company in the past. I'm just trying to let you know that you should feel good collectively as a class, because that's not very common. I think we had 2 or 3 100s in here and then 1 or 2 99s. So once again, overall pleased with the scores. But today what we're doing is we're starting nomenclature in here. And so there was a handout that was up here, and if you came in late, anybody need one of these? Okay. Anybody else need one? Somebody else need one? and the class that's coming up are one of two what I call can't miss classes of the semester. It's not like I do a beautiful job, anything like that, in teaching this stuff. It's just stuff that students that miss these classes today and next week tend to be what I call forever screwed in this course. It's because what we're doing is we're going through chemical nomenclature. And anybody know what nomenclature means? Well, what do you think it means in terms of chemistry? Well, the word nomenclature is a systematic method of naming. So what we're going to do is we're going to learn how chemists come up with these names. So if you see something like a potassium nitrate, or you see something like a sulfur hexafluoride, and we want to know something about its composition, that's what we're going to be doing. And I don't think there's anything magical that I do in terms of teaching it, but what I can say, well, you're the ones here, but the ones that aren't here, they're the ones that may be getting zeros on the next exam on this piece. Okay? So it's just something that you really need to pay close attention to, because the rules that we go through with nomenclature are something that's very specific. Now, with this sheet here, I'm not going to have a separate quiz or anything on this, but this is something that you should have memorized by the time you get to class next Tuesday. So this is a to memorize task. If you don't have this memorized by next Tuesday, then next Tuesday's lecture you're going to be behind on. So again, you need to have this memorized by Tuesday in here so we can kind of keep up with everything that we'll be going through. Now, before we get too far into the nomenclature, one of the things we should be able to do is to know how to interpret chemical formulas. And I forgot to pull my Socrative app up here today, so let's see if I'm logged in. I am. So we'll go over here. We're going to do the quiz. And of course I need to type this. How about nomenclature? I think that's enough. Let's see. Where is it here? There we go, right here. So we'll start this. And I'm going to have you first take a look at this formula, calcium for calcium phosphate, and see if we are able to count oxygen atoms in here. And feel free to talk with a neighbor or whatever on these. Again, our first piece in our success with nomenclature is being able to count atoms. So we're looking at calcium phosphate. So let's get your answers locked in here. We'll count down 5, 4, 3, 2, 1. And there are, in fact, 8. So if we want to get the number of oxygen atoms, what operation are we going to use? Multiplication. So when we see a subscript, that's what we call numbers down below. We call those subscripts. Number values up above are called superscripts. When we see subscripts, those values down below, they are a count. And if we have a quantity in parentheses, that tells us we have to multiply by whatever is inside of those parentheses. So in this case, there'd be a total of 8 oxygen atoms. How many phosphorus are there? Okay, and how many calciums are there? There's 3 calciums, right. So again, step number 1 when we go through nomenclature is to be able to count the number of atoms of each element. And so when you look at it like this, what you should kind of be thinking is you should be thinking when you see a Ca3 that there's 3 calciums, and with the parentheses around the PO4, you should be thinking that there's 2 of these phosphates. Even if you don't know the name of them yet, And so you can see there, if there's 2 of these PO4s, that's telling us there's a total of 8 oxygen atoms in there. Now, as far as the nomenclature goes, spelling is going to be important, just like it was with writing the names of the elements. And so an example we could give of something like this is if we look at the name chlorine, chloride, chlorite, and chlorate. And if we look at these names, notice that as we go from one to the next, to the next, to the next, all we're doing when we go from to the next one is changing one letter. But when we do that, we are changing the composition. Typically when we talk about chlorine, and I think we did this for the last exam, this is one of our diatomic elements. So we'd write the formula for chlorine as Cl2. Chloride represents an ion, and its formula is Cl with a negative charge. Chlorite, when we see an ITE suffix, the formula for the chlorite ion is ClO2 with a single negative charge. And we see it with an ATE suffix that tells us we have ClO3 with a single negative charge. Now, you don't need to memorize these at this very moment, but I'm just bringing this up to show us why spelling counts, because even the difference in one letter conveys different information about its composition. In fact, if you look at the ones that you were asked to memorize, most of these that you were asked to memorize have what in common with the name? Most of these, what do these have in common in the names? Look at their suffix. It's 8. So again, the ones that you are memorizing, most of these here have a suffix of ATE. Not all of them, but most of them do. Okay, now, if you look at all of them here that have an ATE suffix, what do most of these that have an ATE suffix have in common in terms of their composition? They have a negative charge. Now, the amount of negative charge varies, which is part of why we memorize them. And what else do they have in common? Again?
Oxygen.
Oxygen, sure. But again, they have different amounts of oxygen, so that's yet another reason why we memorize, because they have different amounts of oxygen. Now, you might say it would be great that anything that ends with ATE would always have a charge that's 2 negative, or a charge that's 3 negative, or if it ends with H, it always has 3 oxygens. The problem is we're mixing our rules of nomenclature with history. And it turns out when we mix it with history, many of these things were named before we knew their composition, their exact composition. And so when we found phosphorus out in nature, that is like if we were mining it up or whatever, the most common form of phosphorus we found out in nature was phosphate. When we found sulfur out in nature, the most common form we found was sulfate. When we find nitrogen out in nature, the most common form is nitrate. So that's where these things came about, is because they are the ones that are most common in nature. But they were named before we knew the composition. So because they were named before we knew the composition, then we have to live with the set of rules that tells us that different amounts of oxygen and different charges that are part of them. Now, there are going to be some others that you are going to memorize. In fact, if you were to go to your textbook, you'll see a table that appears on page 143. And you don't need to open this right now if you don't have your textbook out here. But do want to point out that on your list of ions to memorize, for example, you will see something like nitrate. Nitrate is right here. But I'm also going to expect you to know the formula for the nitrite ion. And likewise, if you look through your list of ions to memorize, you'll see sulfate on your list of ions to memorize, sulfate right here, but we'll also expect you to know the formula for the sulfite ion. And if you start going through and looking at them, there's no need to memorize the formula for the sulfite ion, just like there's no need to memorize the formula for the nitrite ion. Because if we look, and there's another one up here, like you're memorizing chlorate. You're memorizing this one right here. But you're also supposed to know the formula for the chlorite ion. If you look carefully, again, the ones circled are the ATE. These are your two memorized ones. How do the ITE formulas compare? One less oxygen, exactly. So if you've memorized that nitrate is NO3 with a single negative charge, then the nitrite ion is going to be NO2 with a single negative charge. The charge doesn't change. The only thing that changes is the number of oxygens. Likewise here, if you've memorized that sulfate is SO4 with a negative charge, that means the sulfite ion would be SO3 with a 2 negative charge. So again, the ITE form always has one less oxygen than the ATE form. And the one that you are going to memorize is which one? Eights, exactly. If you memorize the eights, then you'll be able to figure out the formula for the ites. So again, you will need to know that set of rules. Any questions here yet? All right, so now we start looking at the types of compounds that are present. We break down types of compounds into two broad categories. And those two types of compounds are ionic compounds and molecular compounds. So again, ionic compounds and molecular compounds. And when you eyeball them, there's going to be a couple broad categories that these will fit into. First of all, we say that if they are ionic compounds, these involve metals bonded to nonmetals. Metals bonded to nonmetals, and this is going to be with one class of exceptions. And the class of exceptions are what we call ammonium compounds. These are going to be ammonium compounds. This is the class of exceptions we'll work with. So again, in metals, or in ionic compounds, we have metals bonded to nonmetals with one class of exceptions. And that class of exceptions, again, would be ammonium compounds. And you will find that ammonium compounds, notice if you look at the ammonium ion here, how is the ammonium ion different than all the rest of them that you're memorizing? Right, it's the only positively charged polyatomic ion on your list to memorize. And so that's why it is a class of exceptions, because most of the time your metal ions are the ones that are positively charged. But the ammonium ion happens to be one example. It doesn't have any metals in it, and it has a positive charge. Now we compare this to molecular compounds, which this involves nonmetals and or metalloids. So nonmetals and or metalloids bonded with other nonmetals and or metalloids. So again, nonmetal to nonmetal, or metalloid to metalloid, or nonmetal to metalloid. And if we go back to your periodic table, where is that dividing feature? You might as well get your periodic table out because we're going to be writing on these. Let's see if I have some to pass out here. There we go. Anybody need a clean, fresh copy of the periodic table? Heck, just pass it to everyone. If they can never have too many periodic tables. I'll just move to everyone. But yeah, we wrote all over them last time that way. Anybody else need one now? All right. So, what is our dividing feature that separates metals from nonmetals? Where do we find that? Staircase, right. So, remember that this staircase in here separates metals from nonmetals? Where do we find the metals? Left side. And the nonmetals to the right. And where do we find the metalloids? Along the staircase. And there's one exception on this side of the periodic table. Which element is it? Hydrogen. Hydrogen is classified as a nonmetal. Though I think maybe we mentioned that there's some studies that suggest it has metallic properties. If we get it super, super, super cold, turn it into a solid. But generally at room temperature it behaves as a nonmetal. So again, when you look at the formulas, you will want to see which elements are present. Then the second criteria here, even though this is a topic we won't be hitting until our third exam in here, we still need to put down this distinguishing feature, and that is that atoms here are joined by ionic bonds. And this is a case where electrons are transferred. And in molecular compounds, we say that the atoms are joined by covalent bonds. In which case electrons are shared. So with this set of rules, we are going to look at different classes of compounds. And these are the 5 different classes of compounds that you are going to be responsible for naming for this next exam. And these classes of compounds are, first of all, binary ionic compounds. Second category is going to be ionic compounds with polyatomic ions. The third category is going to be binary molecular compounds Number 4 is binary acids. And number 5 is going to be oxyacids. So again, these are the 5 categories of compounds that you will be responsible for. Send it through. Yeah. All right. Okay, next. Let's talk about some of these things. We've already talked about ionic. So these we've defined. We've already defined molecular. So you should know what it means. We should be able to recognize a formula and tell whether they are ionic or molecular. What's another word that pops up in here a whole lot? Binary. Well, what does binary mean? Two. This means we have 2 of something. So these are going to be ones that contain 2 elements. So these are going to be compounds that contain 2 elements. So if it's a binary ionic compound, a binary ionic compound is going to contain 2 elements. And because it's ionic, one of those elements must be a metal, the other must be a nonmetal. If it's a binary molecular compound, there's going to be how many elements again? 2. If it's molecular, that must mean it contains nonmetals or metalloids only. There's no metals in there whatsoever. Now another term we see pop up in here is the word acid. Acid. Well, now, if it's an acid, it turns out that acids are molecular compounds, but what's going to be more important for us to know is that acids always contain the element hydrogen. And that hydrogen is always written at the front of the formula. And I know I just said the word always. We'll find out when we get into organic nomenclature that that's different. But when we're dealing with the class we're working with now, we'll identify an acid by writing the hydrogen at the front of the formula. Then we see the word, so if it's a binary acid is going to contain two elements, one element of which is hydrogen, and that hydrogen will be written where? At the front. Now what do you suppose an oxyacid is? Well, what do you think oxy means?
Oxygen.
Oxygen. So an oxyacid is also going to contain oxygen. It will also contain hydrogen. The hydrogen will be written at the front of the formula. And then our last one here is this term with polyatomic ions. There we go, with polyatomic ions. We've seen the word, if you look carefully today, you've seen the word polyatomic ions somewhere already. Where have you seen it? Lift it up high. Where have you seen it? Right there, yeah, you saw it right here. Okay, now some of you were looking at that before. See the word polyatomic. The word poly means many. So we're talking about many atomed ions. So this is your list of polyatomic ions, or many atomed ions, that you're going to memorize. Remember, before the first exam we talked about ions. We talked about ions as being atoms or groups of atoms that have gained or lost one or more electrons. So now this is a case where we have these groups of atoms, and so these are the polyatomic ions that you are to memorize. Now, the reason why we spend time talking about these different classes is because each class of compounds has its own set of rules. Each class has its own set of rules for naming. And what will happen is that if you start seeing a whole bunch of formulas written down, the temptation is to start naming it right away, but before you start naming it, you have to be able to tell which class it belongs to. And if you can't tell which class it belongs to, you're going to apply a set of rules that belongs to a different class. And so each class, again, has its own set of rules. So to start off with this, I'm going to write down 6 formulas. Here are the 6 formulas. They are H3PO4, HI, Na2SO4, Ag2S, SF6, and Ti, then in parentheses, C2H3O2, outside the parentheses of 4. So now what I'd like for you to do here is to take these 6 formulas and tell which class does each one belong to. They will only belong to one class. So for example, if you think that H3PO4, I'm not telling you the answer, but if you think that H3PO4 is a binary molecular compound, then just write that number next to it. I'm not telling you that's the answer, but go through each one of them and tell which class it belongs to. And these then will be the next ones that come up on the Socrative app. They will come up in order. But talk these over with a neighbor. I'll give you about 3 or 4 minutes. Remember, there's only one classification that will fit for each one. And the first one, the H3PO4, is up on the Socrative app right now. I think the order they appear is left to right, and then the second row left to right on the Socrative app. So I think the one after this is going to be HI. We'll give you about one more minute. About one more minute to discuss the remainder here. Take about 30 more seconds. Get your answers for the first one locked in. You should have the rest of them discussed so we can go through them boom, boom, boom in order. And we'll count down on this one. 5, 4, 3, 2, 1. You can write down your answers. This one here is an oxyacid. Let's talk about what makes it an oxyacid. First of all, why is it oxy? It has oxygen in there. What makes it an acid? Hydrogen where? In the front. That makes it an oxyacid. Can't be a binary acid because? More than 2 elements. Okay, any questions on this one? Next one, HI. HI. Let's get your answers locked in here, please. We'll give you about 15 seconds. And we'll count down. 5, 4, 3, 2, 1. Binary acid. Good. Binary acid because it contains hydrogen written out at the front, and there are 2 elements. No oxygen in there. Next up, Na2SO4. Na2SO4. Give you 5 seconds here to get your answers locked in, please. We'll count down. 5, 4, 3, 2, 1. This one here is an ionic compound with a polyatomic ion. First of all, it's ionic because the elements present are metals and nonmetals. It has a polyatomic ion in there because, for one thing, there's more than 2 elements. More than 2 elements. And then, obviously, you haven't memorized your polyatomic ions yet, but if you work on it, you would see that SO4 here indicates that it is the sulfate ion. All right, next up, Ag2S. Ag2S. Let's get your answers locked in, please. Count down. 5, 4, 3, 2, 1. This is a binary ionic compound. Why can't it be binary molecular? Metal and nonmetal. If it's an ionic compound, it has metals to nonmetals. Silver is not a nonmetal. Silver is a metal. Sulfur is a nonmetal. Next one, SF6. 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 We'll get our answers locked in, please. I'll count down. 5, 4, 3, 2, 1. Hey, wonderful. I'll go to sleep tonight. And then the last one, Ti in parentheses, C2, H3, O2. Outside the parentheses of 4. Locking in our answers, we'll count down. 5, 4, 3, 2, 1. And this is an ionic compound with a polyatomic ion. It's ionic because we have metals and nonmetals. It's with a polyatomic ion. Remember, poly means many. So this portion here is a many atomed ion. You've not memorized them yet, but once you do, you'll see that the acetate ion is up above right here. So, any questions on the classification? All right, ready to name them? Start naming. Let's go ahead. First thing we're going to start naming is going to be binary ionic compounds. Binary ionic compounds. These are the easiest of all of them to name. So again, binary ionic compounds involve metals bonded to nonmetals. And how many elements in the formula? 2. So most of us know the formula of this one, which is NaCl. 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 How about the name of this? Anybody know the name? Sodium chloride. Good. Sodium chloride. So here's how we go about naming these. What we say is that the metal retains its name, and then the nonmetal present in the formula retains what we call its root name, onto which we add a suffix of IDE. So the nonmetal retains its root name, onto which we add a suffix of IDE. And the root name is usually the first 1 or 2 syllables of the element's name. So for example, if we just looked at chlorine, the root name of chlorine is chlor. Then we added a suffix of IDE on, so it would be chloride. What do you suppose the root name of oxygen is? Ox. And so in a compound it would be called an oxide. That's an oxide. If we had something like bromine, the root name would be brome. In a compound it would be bromide. Okay, so that's how we go ahead and name those. So if we then looked at something like Al2S3 and wanted to come up with a name for this one, help me out now. Aluminum sulfide. Aluminum sulfide. And if we did this one, Ba, Br2, this would be barium bromide. And if we did this one, Na3N, Na3N would be sodium nitride. Sodium nitride. And all of these here with the IDE suffix. Now if we want to go in the reverse direction, let's say that we want to write a formula for something like lithium fluoride. Lithium fluoride. Remember that fluorine is spelled F-L-U-O. Lithium fluoride. Now to do these, here's where we're going to write some stuff on our periodic table. These are ionic compounds. And remember when we talked about ions before, ions are atoms that have charges. These are atoms that have charges. Now the charges that they have will depend upon their position in the periodic table. So it turns out that everything here in group 1A is going to have a charge of 1 plus. Everything in group 2A is going to have a charge of 2 plus. If we skip over to group 3A, over here, these are all going to have a charge of 3 plus. And then I'm going to work backwards here, starting with group 7A. In group 7A, these all would have a charge of 1 minus. 6A would be 2 minus, and group 5A would be 3 minus. And actually the 3 minus only applies to these non-metals that are in there. Likewise, the 2 minus only applies to the non-metals, so they might go down to here. So when we talk about the charges, these negative charges only apply to the non-metals that are part of those groups. Now for the rest of the periodic table, we'll talk about these rules in just a bit as to what their charges are and whatever else. But now, if we wanted to write a formula for something like lithium fluoride, we locate lithium in the periodic table. We find lithium right here. We find fluorine in the periodic table. We see it over here. We see lithium would have a charge of 1 plus. Fluoride would be 1 minus. So now with a charge of a single positive, Li with a single positive, F with a single negative, our objective here is to balance charges. We want the total of the positive charges to balance the total of the negative charges. Well, what do you think about them right now? Are they balanced? Yes, they are, because we have a single positive and a single negative. If those charges balance, they in effect cancel out. And the formula we write for lithium fluoride is going to be LiF. And your final chemical formula is always written without indication of charge. Final formula is always written without indication of charge. If you leave charges in here, that is, wrote it like this, it is wrong. You may have had a generous high school teacher that allowed you to keep them in there, but again, that's a generous high school teacher. He or she shouldn't have been doing that. Final chemical formula is always written without indication of charge. I didn't pick this up, and you didn't say that this was Na plus Cl minus. You said it was NaCl. So there's no charges. And we talk about water. It's not H2 plus O, it's H2O. So again, your final chemical formulas do not show any charges in them whatsoever. If you leave them in there, Master Chemistry will mark you wrong. If you leave them in there on exams, I will mark you wrong. So again, final formulas do not show charges. Any questions yet? Yes? That's a good question. The question was about, what about hydrogen that's diatomic? Do we write it as 1 plus? Well, what we need to remember is when we talk about the diatomic element, and we write its formula as H2, that is as a neutral element. When it's in a compound, it's handled differently. So by itself, we write it as H2. If we talk about oxygen by itself, we write it as O2. But in compounds, then they're different. So again, the distinction is, when we talk about the diatomic elements, that is as pure elements, not when they're combined with other elements. Okay? So let's try one example of that. Let's do something like sodium. I think I wrote sodium sulfide. No, I didn't write it yet. So let's just do one that proves this one. Let's look at sodium oxide. And this will hopefully answer your question. I know you asked about hydrogen, but this will show oxygen. So now if we want to show the charges on this one, we locate sodium on the periodic table. Sodium has a charge of how much? 1 plus. Oxide is O with a charge of 2 negative. So when we write these, we write Na with a plus charge, and it's O with a 2 negative charge. We don't write O2, we don't write the subscript down below. It's simply O with a 2 negative charge. So we write it like this. And I think this is what you were asking. Right. So when it's diatomic, that's as a pure oxygen. So like the oxygen we breathe in is O2, but it's O2 not combined with any other elements. Okay. So now, we write a formula here. Our objective is to balance charge. Which type of charge are we deficient in? In other words, which type do we need more of? Positive. How many more positives? 1. So if it helps you, then write it like this. And then when we go to write the formula, we then write them with subscripts. So we'd write this as Na2O. So subscripts down below are atom counts. When we write superscripts up above, those indicate charges. Okay, so this tells us that we have 2 sodiums for every 1 oxygen. Let's try this one here. Again, if you have any questions at any time, just stop me. Otherwise, we look at examples. Let's look at strontium iodide. We go to the periodic table. We locate strontium. Strontium would be Sr with a charge of 2 plus. Iodide would be I with a charge of 1 minus. So we have Sr with a 2 plus, I with a single negative. Then when we write out the formula, which one do we need more of here? Iodide. How many more? We then write the formula as Sr I2. Let's do another one. Let's try magnesium sulfide. Magnesium sulfide. We do magnesium sulfide. We come back to the periodic table. We see that magnesium is Mg with the charge of 2 plus. Sulfide is S with the charge of 2 minus. Mg2 plus, S2 minus. Which one do we need more of? None. So we write the formula as MgS. And if we look at the last one here now, let's look at aluminum oxide. Aluminum oxide. Gotta spell it right though. It's aluminum oxide. So we go back to the periodic table. We look up aluminum. Aluminum is right here. It's going to have a charge of 3 plus. Oxide is right here. Its charge is 2 minus. So Al 3 plus. O is 2 minus. Now we need to balance charges. We can calculate, if we look at the absolute value of these two numbers, we can then find the least common multiple between 3 and 2. Least common multiple between 3 and 2 is 6. So how do we get 6 positive charges? 2 aluminums. How do we get 6 negatives? 3 of the oxides. So again, we have 6 positives balancing 6 negatives. We write its final chemical formula as Al2O3. Any questions on these? All right, let's try these for practice. If I write the name, you write the formula. If I write the formula, you write the name. So we have Li2S. We have Ca3N2. We've got potassium phosphide. And number 4, barium oxide. And these will be the next 4 on the Socrative app. And if you want a challenge, you can do this last one here, EANA2. So again, these will be the next 4 on the Socrative app. The bonus one will not appear there. Again, if the formula is given, write the name. If the name is given, write the formula. Raise your hand. Or top of the finger. The first one, the Li2 acid reagent on the Okay, I'll give you about 30 seconds to get the first answer locked in. You have that one locked in, you should be discussing the rest of them. Okay, and we are going to count down on here. 5, 4, 3, 2, 1. Correct name, wonderful. Lithium sulfide. I think everybody got that. Super. Next one. The name of the compound, Ca3N2. Ca3N2. Let's get your answers locked in, please. And we'll count down. 5, 4, 3, 2, 1. All right, calcium nitride. Remember, if it has ATE suffix, which element must also be there? Oxygen. No oxygen in there. We haven't talked about naming those with 8s yet. All right, next up. Formula for potassium phosphide. And we're going to count down. 5, 4, 3, 2, 1. K3P. Any questions on this one? Very good. And then the last one of these, the barium Oxide. Write the formula for barium oxide. We'll get the answers locked in, please. Count down. 5, 4, 3, 2, 1. And this would be not BRO, but BAO. BAO. Any questions on these four? Anybody get the last one? Okay, anybody see a problem with this last one? Two metals, which means it's impossible. Unless you want to be funny, you call it a banana. And of course, you already learned about what K3P is. Anybody know what K9P is? Uh-huh. Also known as dog urine, right? Just say the word K9P, for those of you that are a little slow. All right. Any questions? I don't put those on exams. That's just to say I prefer my day job. All right. Next up, let's look at these. We left off the elements that are the transition elements down below here. And that's because these here, I'm going to put these in a different color now. If you have like a pen or pencil, something different, you might want to mark these differently. These that are in here have what we call variable charges. These here have variable charges. And there are 3 exceptions to those variable charges. Those 3 exceptions I'm going to put in blue to be consistent in my color scheme. These here are the exceptions. They're the zinc, cadmium, and silver. And that means you need to memorize these 3 charges. And anybody know how you might already know that or to memorize these? All right. Take up the sheet that you got at the beginning of the hour today. You're going to see the silver, cadmium, and zinc on here. These 3 are ones that you need to memorize. And their charges on the silver is a single positive. On the zinc and the cadmium, it would be a 2 positive. All of the rest of these in here have variable charges. Then it turns out that there are some elements under the fixed charge area that actually have variable charges, and that would be these right here. These here also have variable charges, so the variable charges includes these here, but it also includes these that are boxed in below here. And these have, once again, variable charges. Now, all you need to know is that they have variable charges. You don't need to memorize what those variable charges are. In my day we did. In our day today we don't need to. And that's because we have a convention that helps us keep these straight. And for example, we can talk about the iron 2 ion and the iron 3 ion. And by the way, these are Roman numerals. These are Roman numerals. And for some reason, people have trouble writing Roman numerals into mastering chemistry. Just so we're clear, what is each one of these letters? I. Right, it's a capital I. Okay, so I see people writing L's and the vertical line feature. They're capital I's is what they are. So make sure that you get them in correctly. If we have an iron 2 ion, and by the way, these are parentheses now. There's no space in them, so it's not iron space parentheses. It's written with no spaces as you write those names into mastering chemistry. An iron 2 ion is Fe with a 2 plus charge. What do you suppose an iron 3 ion is? 3 plus, exactly. And if we look at Cu with a single positive and Cu with a 2 positive charge, Cu with a single positive charge, what do you suppose this one's called? Copper 1, and this one would be copper 2. So very simple, the Roman numeral is equal to the charge on these ions. So in any of these here that have a variable charge, if we just write the Roman numeral, for example, if I wrote Mn2 positive, Mn2 positive is going to be manganese 2. We'll write the same as manganese 2 with the Roman numeral in parentheses. So manganese 2, again with the parentheses. Now, sometimes these hold on to their historical names. You're not accountable for the historical names. But if they were, the historical name for this one here, I'll put it in a different color. The historical name of this one is the ferrous ion. And this one here is the ferric ion. The old name here is the cuprous ion. This one here is the cupric ion. Well, you see, back in the day, and some of these will still are still written this way. For example, when my ex-wife was going to have a baby, she was low on iron, so when she took the supplements, she wound up taking some ferrous sulfate. Okay, we went to the store, bought some ferrous sulfate. So we didn't call it iron 2 sulfate then. If you go and pick up an iron supplement today, you'll see something like a ferrous gluconate or a ferrous sulfate, yes. No, it won't be, but I do bring it up because you may still see them out on the shelves and stuff, okay? So your text does not use these that are in red, but I bring them up because you may still see them out there. And part of the confusing piece about this is, notice that we have different suffixes. We have an OUS suffix and IC suffix. And the cupric ion, the IC, and an IC here, these have different charges. And furthermore, if we look at the 2 plus here and the 2 plus here, this is an OUS and that's an IC suffix. And so it was very easy to get them mixed up. So this is one where it does have a historical basis, but we found a way to fix these names. We have not found a way collectively to fix names like nitrate, sulfate, and whatever else. And for the positive ions we have. So now, when it comes to writing formulas for these, if we have something like iron 3 oxide, we want to write a formula. Iron 3 is going to be Fe with a charge of 3 plus. Oxide is going to be O with a charge of 2 negative. So now we like to balance charges. How many irons are we going to need altogether? 2. How many oxides altogether? 3. So there's 2 of the 3 positive, there's 3 of the 2 negative. That means our final chemical formula is going to be Fe2O3. Versus if we look at the formula for iron 2 oxide, iron 2 oxide would be Fe with a charge of 2 plus. Oxide is O with a charge of 2 minus. So the formula here would be FeO. Let's try another one here. Let's try titanium 4 sulfide. Titanium 4 sulfide. So titanium 4 would be
4 plus.
Ti with a 4 plus charge. Sulfide now, based on its position on the periodic table right here, would be a charge of 2 minus. Which one of these two do we need more of?
Sulfide.
Sulfide. How many more? 1. So the formula for titanium 4 sulfide is going to be TiS2. Remember, the subscripts are a count of the number of atoms of each element. Yes?
So whenever we see Roman numeral, we can assume that X and the non-positive.
That is correct. Yes. And the ones that we include Roman numerals on, and only the ones that we include Roman numerals on, are the ones that have variable charges. If it has a fixed charge and you include a Roman numeral, for example, now that students learn Roman numerals, I like to see them, they want to apply them all the time. So we don't go back where we started here and say that this is strontium 2 iodide, this was strontium iodide. So the only time we include those Roman numerals is when multiple charges, variable charges, are possible. Okay, anybody else? Okay, now we sometimes have difficulties going in the reverse direction. Let's say we have CuO and Cu2O. We want to write these names. I'll give you a couple minutes here. Give you a couple minutes. Now, because copper is one of those elements that has variable charges, that means we must include a Roman numeral in its name. I expect to see some mistakes on this one, so compare with at least 2 people. Compare with at least 2 people. Please don't stare into space. Compare with at least 2. All right, let's check these out. Just give me a finger, 1 or 2. All right, first one, how many? 1 or 2? All right, it is copper 2, good. And next one is copper 1, copper 1. Okay, now, do you see why sometimes we mix these 2 up? Sometimes students will see this formula and want to call it copper 2. But where does this Roman numeral come from? It comes from the charge. And that's because oxide always has a charge of 2 negative. If oxide always has a charge of 2 negative, in this case that must mean it's balanced by a charge of 2 positive. In the second case it must be balanced with copper with a charge of 1 positive. But it takes 2 of these to balance the charge. All right, here's a preview of next Tuesday, because I know you want to work over the weekends. Well, not all of you want to, but it's a necessity for some of you. So let's just do a quick preview of what's going to come next Tuesday, and so you can get some work done on your homework. let's say that we look at something like potassium nitrate. We're going to move on to the second category here right now. The second category is ionic compounds with polyatomic ions. Ionic compounds with polyatomic ions. And let's say that we look at something like potassium nitrate. Potassium nitrate. Notice now that our suffixes are different. Once you see a suffix of ATE, that should trigger something in your brain that says to memorize. These are your ones that contain oxygen. So these are your polyatomic ions that list we passed out right at the very beginning. Here's your nitrate. So to write the formula, we do just like before. We want to balance charges. Nitrate is NO3 with a single negative charge. NO3 with a single negative charge. Potassium comes from its position in the periodic table. Potassium's charge is going to be 1 plus. So now if we have a single positive and a single negative, what do you suppose happens to charges? They're going to cancel out, and the formula will be KNO3. And let's say we had something like this one here. Copper 1 carbonate. Copper 1 carbonate. Again, you're going to see that ATE suffix. That should trigger something up here that says, I memorized it, it contains oxygen. Of course, you probably don't have them memorized today. But if you come back here to carbonate, you see carbonate is CO3 with a charge of 2 minus. So if you see the CO3 with a charge of 2 minus, we're then going to combine it with copper 1, which is Cu with a charge of 1 plus. So now to balance charges, how many coppers are we going to need? 2 of them. How many carbonates are we going to need? 1 of them. The formula is going to become Cu2, CO3. So this is the stuff we are going to be working on come the next class. I do have a worksheet here. Now I hesitate passing it out today because you're not going to know more than about maybe 5 on here. This is not going to be a worksheet that I am going to collect from you. Answers for these are on B12, right space. This is for people that want to really start on the rest of this nomenclature stuff, because otherwise it's going to feel like we are chasing the bus or whatever on Tuesday. When it comes to nomenclature, treat it like learning your multiplication tables in elementary school. Remember those? You probably did them every year. So this is something to practice, practice, practice. If you think you got it, you don't. You have to practice it until you know you got it.